Our very distinguished invited guest, Honorable Professor Prafull Kumar Jha of the MS University of Baroda, Vadodara, and Honorable Dr. Uday Kumar of National Institute of Technology, Jamshedpur. My own distinguished colleagues, Dr. Vibhuti Shekhar Lal Das, HOD, come convener of this webinar, Professor Ajit Kumar Chaudhary, who is also the proctor of LM Mithila University, other honorable teachers of the department, Professor Ashok Kumar, Dr. S.M.A.H. Normani, Dr. Lakshmi Kant Jha, Dr. Satish Chandra Thakur, Dr. Raj Kumar Chaudhary, and other teachers of the college who are in the audience. This gives us much pleasure to welcome the distinguished guests and the distinguished members in the audience. So far as the topic is concerned, it would be dealt with in detail by the speakers, managing secretary, and convener of the program. My job is to welcome the guests. In 1928, Sir C.V. Raman, a young man from the town of Tiruchirappalli in Tamil Nadu, on the occasion of Indian Science Day, that was later declared as this Indian Science Day, it was 28th February, described to a group of scientists in Bangalore the phenomenon that would win him India's first Nobel Prize for science. Since then, the spectroscopy developed on the principle of Raman effect, wide range of applications in the field of living and non-living world of science and day-to-day life. These are the implications of his findings. As per the topic, our honorable speakers of the day will elaborate the applications of Raman spectroscopy in material science. In fact, this technique has also applications where microscopic, non-destructive chemical analysis and imaging is required. Chemical composition and structure of samples, whether solid, liquid, gas, gel, slurry, or powder. The spectroscopy is also used to identify and test the purity of gemstone materials. Raman scattering is a phenomenon in which incident photons lose or gain energy via interaction with vibrating molecules in a sample. The energy shift is used to obtain information regarding molecular composition in a sample with very high accuracy. Raman spectroscopy has been applied for the analysis of biological samples during the last few years. The technique has included quantification of biomolecules, microstructural molecular engineering of cells and tissue, medical diagnosis, and other works in the field of biological science and medicine. It is also used in quality control in pharmaceutical industry, such as active pharmaceutical ingredient in drugs. In the present day corona situation, trade has been banned with China, and most of the active pharmaceutical ingredients were imported from China. Now this has been banned, and it is high time our own personnel working in the field of drug discovery, drug manufacturing, they have now the use of this India-made discovery, and it for becoming significant in the present day corona crisis also. Physicists continue to tweak this more powerful technique while being on the lookout for new applications and new ways of observing the Raman effect closely. Joining the ranks are the two groups of scientists, one from the Institute of Science in Bangalore and the other from Advanced Scientific Research Institute in Bangalore and the University of Mysore. The technology developed by them can identify dangerous substances such as improvised explosive device, IED. On the other hand, blue color of sky and seawater in day-to-day life are few examples of this effect. So with this, I close my address and I welcome all the distinguished guests and other members of the audience. Thank you.
Thanks to our principal, chairman, this webinar. Now I am going to introduce. Yes, telling about. I am introducing how to introduction of Raman Spectroscopy for material science टॉपिक पर मैं कुछ इंट्रोडक्शन इसके बारे में रख रहा हूँ एज ऑर्गेनाइजिंग सेक्रेटरी. Raman spectroscopy is based upon the interaction of light with the chemical bonds within a material, which provides detailed information about chemical structure, phase and polymorphy, crystallinity and molecular interaction. In Raman spectroscopy, a beam of photons, usually with the wavelengths in the visible region, from a pulse laser impinges on a surface. The photons are scattered by molecules within the sample and give up energy corresponding to vibrational levels within the scattering molecule. The scattered photons are analyzed by a spectrometer, yielding a spectrum showing the energy losses, which are characteristics of the molecule with which the photons interact. In recent times, its application is widely used in material science to know the chemical structure and identity, phase and polymorphy, intrinsic stress, strain and contamination and impurity of the specimen. Today we will enhance our knowledge through this webinar how it is used in the field of physics, especially in the material science, from the resource person. The Raman spectroscopy was developed in Lily under the direction of Professor Michael Chai and Edward E. Silva and was commercially produced as the mole. The microscope was initially integrated with the scanning double grating spectrometer, which, when high sensitivity, low noise, multi-channel detectors became available. Triple stage spectrograph were introduced with the microscope as an integrated component. In 1990, the holographic notch filters were demonstrated to provide superior laser rejection so that a Raman microscope could be built on a single stage spectrograph and provide enhanced sensitivity. Compared with the original scanning double monochromatic collection time for comparable spectra, more recent developments in the Raman technique include a simulated Raman scattering, surface enhanced Raman scattering, field enhanced Raman scattering, integration with electron microscope and atomic force microscope, hybrid single band system, as for example Raman PL, epifluorescent photocurrent transmission Raman for through bulk material analysis. Today, it is based in a various fields like art and archaeology, characterization of pigment, ceramic and gemstone, carbon materials, structure and purity of nanotubes, defect, disorder characterization in chemistry, structure, purity and reaction monitoring, in geological field, mineral identification and distribution, fluid infusion and phase transition. In large scale, single cell and tissue drug interaction, disease diagnosis, in pharmaceutics, current uniformity and component distribution, semiconductor purity, alloy composition, intrinsic stress strain microscope, Raman spectra can be acquired from nearly all samples which contain true molecular bonding. This means that solid, powders, liquids, gels, and gases can be analyzed using Raman spectroscopy, but in general, it is not suitable for analysis of metals and their alloys. Today, we will acquire a lot of knowledge about this from our two resource scholar, resource person, Dr. Praful Kumar Bhaji एवं डॉक्टर उदय कुमार जी। मैंने विषय पर भी उसको रखा। अब इसके साथ मैं डॉक्टर उदय कुमार की का बारे में कुछ बताना चाह रहा हूँ, जो इस विषय पर अपना प्रकाश डालेंगे। Dr. Uday Kumar is at present working as assistant professor in Department of Physics, NIT Jamshedpur. He obtained his PhD degree in the year 2003 from Institute of Chemical Technology, University of Mumbai. Dr. Kumar also worked as senior scientific officer from July 2007 to 2018 at IISc Kolkata. In addition to this, Dr. Kumar also served as visiting scientist and research associate at Milano University, Italy, Athens Bose National Center for Basic Science, Kolkata. He has published 25 research papers in international journals and presented 7 papers in international conference. He is also a research member of Laser and Spectroscopic Society of India and JRC Scholarship holder during his PhD work besides reviewer of some international journals such as Journals of Non-Crystalline Solids. डॉक्टर कुमार का कैरियर आप हमने डिटेल्स दिया है, कुछ पोर्टल को रखा हूँ और ये उनका कैरियर बहुत अच्छा रहा है। अब मैं चाहूंगा कि डॉक्टर उदय कुमार से रिक्वेस्ट है वे अपना ये व्यू इस पर रखें और टॉपिक के बारे में हम लोगों को विस्तृत जानकारी देंगे। डॉक्टर उदय कुमार।
Hello. Good morning, good afternoon, everybody. Hello.
Yes.
Sound barabar.
Am I audible?
Yes, yes. Okay.
So, Dhanyawad, sir.
Namaste.
And good afternoon, everybody. So, let's start the topic over here of interest, our Raman spectroscopy and instrumentation and applications entire. So, first of all, let me briefly explain the field exactly. Raman spectrum, let's start the basic characteristics of the material, and for that, start from basically this is subject matter related to the interaction of light with the material. Basically, material is comprised of, if you look into the problem of band structure. So let's start the understanding starting from the band structure. So electronic band structure and which consists of also rotational and vibrational degree of freedom. So I will share you one of the slide, and therefrom I will start the real things which you can understand. So basically, electronic ground state is mostly almost represented by S0, and a higher energy state is represented by first excited state as second excited state, almost by S1, S2, S3, theoretically up to the nth state. And each of the electronic state is comprised of a large number of states separated to each other. If separation is larger, almost that is in those are called vibrational level, and each vibrational level is comprised of a large number of small energy level, which is called rotational level. So actually, This Raman effect is associated with all these three kinds of energy scales: electronic, vibrational, and rotational. All those things. It is also associated with the atoms and molecular system as well. I'm not able to connect this thing. Ah. Okay. So let me share. No. Oh, sorry. Just a minute, please. Spare me with me. Sorry. Just a minute here. Yes. And now, say. Oh, I'm unable to share this PPT file. This is the problem. I don't know. Why this is not being shared, I don't know.
Your present now option is not working, sir.
हाँ सर, एक्चुअली पीपीटी है जो मैं शेयर करना चाह रहा हूँ, वो आ नहीं रहा है, आई डोंट नो क्या हो रहा है।
प्रेजेंट नाउ पे एक काम कीजिए सर, प्रेजेंट नाउ पे प्रेस कीजिए और
हाँ,
उसके बाद आप
हाँ उसी में देख रहा हूँ, मैं उसी में जा रहा हूँ। वो आ ही नहीं रहा है, इसमें जो है ना शेयर करना चाह रहा हूँ, इसमें कुछ दूसरा चीज आ जा रहा है। वो जो स्लाइड है ना वो आ नहीं रहा है, वही समस्या हो रही है। प्रिंट मोड में ठीक है, देखता हूँ ना, वो आ नहीं पा रहा है सर, पता नहीं क्या हो गया है वो।
परमिशन की जरूरत नहीं पड़ेगी मृत्युंजय।
हाँ वही मुझे भी लग रहा है, पता नहीं क्या है। वो पीपीटी मेरा ओपन है बट आई एम नॉट एबल टू शेयर दिस थिंग, दैट इज द प्रॉब्लम। आई डोंट नो हाउ टू रिजॉल्व इट। चलिए देखते हैं, एक बार फिर ट्राई कर रहे हैं। ठीक है, देख लेता हूँ एक बार। हाँ अभी आ गया है सर। सो इट इज विजिबल, स्लाइड फॉर विजुअल सर, स्लाइड फॉर विजुअल।
नहीं सर, पहले आपको प्रेजेंट नाउ करना है।
अभी आ रहा है
ना?
जी हाँ जी हाँ।
So this is the basic Raman spectroscopy. That about I would like to convey with something. So see, actually, as I told you, कि Raman spectroscopy basically is a subject matter related to the interaction of light with the matter. So you see, these are the so basically this is the molecule, you can say, and incident radiation. So if some incident radiation is falling on an atomic or molecular system, so what happened? Various kind of phenomena may take place. First of all, light may be transmitted totally. A fraction of light may be reflected back, and scattered, being absorbed. So basically, all these physical processes simultaneously may take place. Here what happened? So basically, if light falls, then this is, suppose this state is basically a first electronic state represented by S0. And this S0 is divided into so many large number of energy states. Those are called the vibrational state. And each vibrational state is associated with some kind of quantum number that is called a vibrational quantum number. So starting from theoretically from V is equal to 0 to V is equal to n. So here for simplicity we have shown only V is equal to 0 to V is equal to 1, and again just it is aspirated here V is equal to 2, V is equal to 3, like that. And each of this band I am talking about, V from V is equal to 0 to V is equal to 1, again from V is equal to 1 to V is equal to 2, then again 2 to 3, all these are continuously. So each of this vibrational band is split into so many small energy levels, and those are each level in between the 0 and 1 or 1 and 2 and 2 or 3 are known as rotational levels. Now what exactly? So I'm talking about the suppose the molecule absorbs photons from here. This is S0 and come up to next energy level, electronic energy level, that is here somewhere represented by E1. So this E1 is the first excited state electronics energy, and this is the F0 represented by the F0 and ground state. So ground state is also comprised of a large number of vibrational state, and each vibrational state is comprised of a large number of rotational state. And a similar kind of structure is having each electronics state, higher states, S1, S2, and theoretically existing up to Sn. So what happened? If your excitation energy is sufficiently large, so how much it large if you are zero, and associated with the first electronic excitation how much the pumping energy we should provide to these molecules. So basically E1 minus E0 will be the difference of the energy in between the two consecutive electronic state. Now use the Planck's rule, according to which E is equal to H into nu. So H nu is equal to E1 minus E0. That is H nu is equal to delta E, where delta E is the difference of E1 minus E0. Now nu is the frequency of the incident radiation. So nu is equal to how much? Delta E divided by H. So in this way you can calculate the frequency of the excitation or frequency of incident radiation. So that is quite selective depending upon the delta E, which is the delta E is the characteristics of any atom or any molecule. If you change the molecule, then this gap, this is called the energy gap, electronic energy gap. And that energy, electronic energy gap, is the inherent property of the atomic system or molecule, which changes from one atomic system to the other or one molecular system to the other. Now, in this way, you can have the answer which incident, which wavelength source I should choose for exciting the system. So this is the process. Now, come to the point. What happened? So, if the energy of this incident radiation is equal to delta E, then molecule or atom from this ground state will be excited to the higher energy state, and it will gain the position in any of the electronic state higher than ground state, maybe S1 or S2. Now suppose your excitation energy delta E is quite large. It is possible that from ground state it can reach to the second excited state S2, S3 and S4 and so on. Suppose you have heavily excited with the high energy, then it may reach to the S3. What happened from there? There are two ways. One is it is reaching to the lowest of the S1 state. Another way, if more than enough energy you have supplied, it may go to the any of the highest energy state. From there, what it will do? It will relax slowly, without making radiative transition. So what is radiative transition? Now I will tell you briefly. So from there it relaxes without making any radiative transition. Slowly it will coming down, and then it will where from up to which stage it will continue this attitude. So the lowest energy, the lowest vibrational state of this first excited state at S1. And now from here, without losing any energy in the form of radiation. So that's why this process, this optical process is called relaxation, basically optical relaxation. And from here, there are 2-3 ways. One way, suppose it is a molecule is directly coming from this to this state, then it will radiate energy in the form of electromagnetic radiation, and then it will come to the ground state, because ground state is the lowest energy where the system is quite stable. So this is the process is called fluorescence. This is called fluorescence. Another way, suppose for all these are singlet state. Why we are writing telling that F0, S1, S2, S3? Why we are not telling something else? Because this is singlet state, and that's why it is represented by the first alphabet of word singlet. So ground state is singlet, excited state, all those are singlet. Now there is a possibility that other type of energy state, those are called triplet state, might be existing in the vicinity of all these higher energy states. In the sense, suppose this is the S1 state, may be possible the T1 state, which is first triplet state, might be existing very close to this lowest vibrational state of the first electronic excited state. Suppose over here, and this T1 state is very close to this one, gap is very small. What can happen? And so small, this T1 state and S1 state difference is close to the thermal energy. So how we can define the thermal energy? So suppose that room temperature is T and Boltzmann constant is K. The multiplication of this Boltzmann constant and the temperature is defined as a thermal energy. So this is if this difference, in the sense difference of T1 state, which is close to this one, and this is lowest level of the S1. If the difference of this and this is quite small, and that is comparable to the KT values, which is thermal energy, what happened in that situation? The molecule which is over here in the lowest vibrational state of the first excited electronic state, it will simply by absorbing energy from the KT thermal energy, it will get entered into from the singlet state to the triplet state. Now, if once molecule get entered from singlet to the triplet, what does it do? From here, it can do various routes. So one by one, I am telling you. So from here, triplet state.
सर आवाज नहीं आ रही आपकी। हेलो,
आवाज नहीं आ रही।
उदय सर आवाज नहीं आ रही आपकी। उदय सर, विभूति सर, एक बार कॉल करके रिमाइंड करना होगा, सर को बताना होगा कि सर की आवाज नहीं आ रही है।
मोबाइल से कॉल करता
भारतेंदु जी प्रेजेंट नाउ ऑफ कीजिए। भारतेंदु जी अजीत सर, अजीत सर क्या बात हुई क्या सर?
फोन नहीं उठा रहे हैं, वो रिंग हो रही है।
तो एक काम करते हैं ना, फिर जो इसको ये सर को बुलाते हैं, प्रोफेसर को बुलाते हैं। फिर हो सकता है कोई टेक्निकल प्रॉब्लम आई होगी उन।
वो तो कहते हैं टेक्निकल फॉल्ट हो।
हाँ
और हम अपने शेड्यूल के अनुसार आगे बढ़ते हुए मैं कॉलेज डॉक्टर प्रफुल्ल कुमार झा जी का एक्सपेरिमेंट्स जो है टॉक्सिटी उसको मैं पढ़ रहा हूँ। उसके बाद वो आएंगे तो बाद में हम लोग आवाज आ रही है। हाँ हेलो। हाँ प्रोफेसर प्रफुल्ल कुमार झा is presently professor of condensed matter physics at the Department of Physics, MS University of Vadodara. He has also served MK Bhatnagar University, Bhavnagar, India as co-professor for about 6 years. He received his master's degree from the University of Pune in the joint TIFR UGC Pune University program and PhD from TU Bhopal. He has received several
सुधीर सर, आपका भी माइक ऑफ हो गया, ऑन कीजिए उसको। सुधीर सर माइक ऑन कीजिए, आपकी माइक ऑफ हो चुकी है।
आ रही है आवाज?
अभी आ रही है।
इससे पहले नहीं आ रही थी क्या?
ना, इसके पहले नहीं आ रही थी।
जो तो मैं पढ़ रहा हूँ, मैं रिपीट कर रहा हूँ।
अच्छा, मैं शुरू कर दूं क्या? चलेगा, कोई बात नहीं।
प्रोफेसर प्रफुल्ल कुमार झा is presently प्रोफेसर ऑफ कंडेंस्ड मैटर ऑफ फिजिक्स एंड
आपकी आवाज प्रॉपर नहीं आ रही है अजीत सर, आपकी आवाज प्रॉपर नहीं आ रही है।
अच्छा, देखिए, he had also served MK Bhavnagar University, Bhavnagar, as full professor for about 6 years. He received his master degree from the University of Pune under joint TIFR UGC Pune University program and PhD from BU Bhopal. He has received several recognition awards such as postdoctoral fellowship by the Ministry of Education and Culture, Government of Spain. Professor Jha is an Indian National Science Academy Teacher Awardee for year 2018. He received prestigious PWS UNESCO Associateship Prize and regular Associateship of International Center for Theoretical Physics, Trieste, Italy. His research deals with the complexity issues and key global challenges using the wide range of disciplines such as from core metals to environmental hazardous gases for the prosperity of global. Mainly, his research work focuses from theory, fundamentals of physics to application in the field of drug designing to cure cancer, bioconjugation for the delivery of neurotransmitters, oxide-supported heterogeneous catalyst for the application in fuel cell, semiconductor nanowires, superconducting, geological with extreme environmental, thermoelectric materials for energy conservation conversion, perovskite for the solar cell efficiency and nuclear materials such as a direct impact to tackle developing world's greatest challenges. He has published more than 20 research papers in the reputed journals and serving as member of the editorial board for several journals. 17 students have been awarded doctoral degree under his guidance and 8 are working for the degree. Professor Jha has completed 20 research projects including 5 international from major funding agencies. His index is 30 with citation about 3,350. मैं डॉक्टर प्रफुल्ल कुमार झा जी को समय देने के लिए और इससे जुड़ने के लिए सन ऑफ सॉइल हम लोग के गौरव है। आई को खास करके जो अपने धरती से प्रेम है इसके लिए बहुत बहुत साधुवाद देता हूँ और स्वागत करते हुए मैं इनके सार्वजनिक तथ्यों को जो ये विशेष रूप से ये विषय वस्तु को रखेंगे उनको हम लोग उनसे लाभ उठाएंगे। डॉक्टर प्रफुल्ल कुमार झा जी।
ओके, धन्यवाद सर, धन्यवाद प्रोफेसर अजीत चौधरी जी। At the outset, I would like to thank Professor Vidyanand Jhaji, Principal, Mlsm College, and I have very high regards for him. I have visited this Mlsm College several times, and I had interaction with him several times. Recently also, I had interaction with him on through video conferencing on some other issues. And I also thank Mrityunjay, for approaching me for delivering a lecture. I thank him because I always feel very pleasure presenting my research work or discussing or suggesting whatever way I can do to my native, and that is what is always pleasure for me. And of course, even in this lecture, when he contacted, I agreed and I gave him the time for this particular date on 3rd. And though later on I realized that I have a class at 11:30 to 12:30 on this date and then some other engagement, but anyway, I promised him and I am here, and because it gives me great pleasure, right? And that is why I am here, and I want to present something which I do normally, because this is something Raman Spectroscopy. I am basically, as far as training is concerned, I am a theoretical physicist. I was doing in my early career a lot of phonon calculations for the solid state physics or in the solid, and then it got traversed from the solid to the nano structure, and now I am doing it for many systems, variety of systems. And therefore, in somewhere in between, I also got interested in Raman spectroscopic study. And then, in fact, I started doing, and at this moment, this is also one of my very active area of research for material science characterization. And since, as I said, that I am doing also theory, so my work basically deal with both theoretical aspect and Raman spectroscopic measurements, and of course then several other things will be there. The first lecture, right, in fact, on the same topic, if you have many speakers, then the speakers who come last, it's always a loss, because many general things have already been told. And Dr. Uday Kumar, in fact, he could not complete it right now. I will hope he will complete. But he started very nicely by giving the importance of Raman spectroscopy. That is basically the fundamental thing, that how energy, etc., will be decided and how it comes. And therefore, my particular topic is basically right from the fundamentals of Raman spectroscopy to its application in various fields, right? Of course, topic is related to the material science and then physics. And I heard saying Mrityunjay in the beginning that this is something physics and others may not understand. I should tell him that this technique is something which is being more used by the chemists, and in fact the life scientists should certainly use it, because this is no, it is not that traditional Raman spectroscopy which only physicists can understand. But there is a difference in the sense that just recording any spectra is not the science, and when we want to analyze it particularly in that sense, the physics certainly helps, right? And I hope that is what is meaning. So now let us come to the topic, and let me share my screen first, whether it, but he was also facing the problem, so let me, I don't know. Right. But that is problem. Entire screen. Right. Right, is my screen visible? Can you all see the screen? Yeah. Yes?
Yes, sir.
Yes or no?
Yes, sir.
Okay, fine. So as you can see that the topic of my presentation is Raman spectroscopy for material science, that is an emerging field in physical science. As I said, that it is not an emerging field now only in the physical science, it is an emerging field in all branches of science, and that is why I will be taking few examples from almost all major branches of the physics. And this is what is the beauty of Raman spectroscopy. That is, when it started, it was, of course, you can say it is physical science thing, but now it is no. Dr. Kumar was describing something related to that, so therefore I will exactly not repeat those words, but at least for a couple of slides or 2-3 slides will be something which basically corroborates his presentation. See what happens when you have a sample that is material, here in our case, right? Then we incident light, and then the scattering of light takes place. And this scattering, or in fact you can say the scattering of light from the molecules, and this can be elastic as well as inelastic. When you have the elastic, that means it is Rayleigh scattering, and when it is inelastic, then it is Raman scattering. Since in elastic scattering there is no change in the energy, no change in the wavelength, and therefore this scattering does not give any information, or as you can say, this is of no use. But when you have the inelastic scattering, which I was telling as the Raman scattering, because he defined the Raman scattering. So when you have the inelastic scattering, that is Raman scattering, and this is an inelastic scattering, and therefore there is a change in the energy, there is a change in the wavelength, and therefore this gives a lot of information regarding the material, right? That means when the light interacts, or the visible range, of course, that interacts with the material, there is a change in the energy, and this change in the energy basically gives many information regarding the material. And anyway, this was first postulated theoretically by a Russian scientist, Esmekel, in 1923, but was first discovered experimentally by Sir C.V. Raman in 1928 in an experiment using the sun as a light source. And then in 1930 he got, and this work was published in the Nature journal, and then this he got Nobel Prize in 1933. And that was the basically first point. But now it is a Raman spectroscopy is a very powerful tool and has been around for more than 80 years now, right? And with the advancement in the laser sources, advancement in the spectrometer, detectors, optics, computation, etc., now it has great applications in chemistry, it is in material science, in forensic, astronomy, nanotechnology, biology, and everywhere, right? Many people are working at this moment basically to have the corona test. Of course, since it is corona, it is very dangerous, so it has not come into the existence. But people have used this Raman spectroscopy technique to identify or to test the dengue patient, to malaria patient, and cancer patient, and all other things. So it has a very wide application. And as far as I am concerned, I can say that for the material science, after XRD, right, this is the most important technique for the characterization of the materials property, right? And therefore, now we will move further, and just one simple thing that we know that, of course, we had many great minds as far as science is concerned, but these four people have great contribution. That is Vikram Sarabhai, Sir C.V. Raman, then the Homi Bhabha, and the J.C. Bose, right? And of course, I don't say that there are no more and no others have contributed, but these are the four which have contributed a lot, right? Vikram Sarabhai, we know that he's the father of Indian space program. Sir C.V. Raman gave the Raman effect, and this is Nobel Prize. He won the Nobel Prize in 1930, and I will show you that how important his contribution or how important is his research for the material cell at this moment. Homi Bhabha is anyway known, J.C. Bose is known. So these are basically, and some pictures related to the C.V. Raman's memories. I will not go into this. As I said, that his far-reaching contributions revolutionized the science, right? And first paper published with the title, A New Type of Secondary Radiation, that is scattered radiation. And as I said, it was published in Nature in 1928, for which he got the Nobel Prize in 1930. What it is, right? Why it is a new type of secondary radiation. So you have this as some molecules, you can say. You will incident a light that is lambda with a wavelength lambda. Then there is a possibility that it will get transmitted, it will get scattered, it will get many other things will happen. But the important is that it gets transmitted and it gets scattered. So when it gets scattered, then you will have the wavelength lower than the original wavelength and higher than the original wavelength. So when the wavelength is lower than the lambda gauge, the original, then it is known as anti-Stokes or Raman effect. And many of the devices basically nowadays work in this mode. Then you have the elastically scattered, which I told that it is the relay scattering. Then you will have the fluorescence, and this is very problematic thing when you have the biomolecules or maybe the organic molecules, and therefore a selection of a particular or a certain wavelength is important, and that is what Dr. Kumar was speaking. And then you have the Raman scatter, that is Stokes, in which the lambda is greater than lambda is less. So Stokes are red shifted and anti-Stokes are blue shifted. So first application were of course limited to physics and chemistry. That is what I told in the beginning, to study the vibrations and structure of the molecule. But now there is no case in which it has no application. So it is useful, sorry, material and nanoscience, life sciences, earth and planetary sciences, art and archaeology, forensic science, and several other. I don't know how long I will be able to, or how much thing I will be able to cover, but certainly I will give at least one example for all these things. Right? This is basically importance that the growth in Raman spectroscopy publication by year, and this is of course it can go. The data was only up to this point I could get, so it is plotted. But the point is that you can see that it is increasing, right? And it when suppose in 2003 when it was something 2,500 publication, in 2012 it got up to the 6,000. Then the number of publication in different field, right? In the lower part you can see that it starts from the chemistry to applied microbiology, right? So there is no area of science where science, even I said that art and archaeology and other things. So there is no area in which Raman spectroscopy cannot be used. But the major contribution of Raman spectroscopy comes in chemistry, material science, physics, technology, engineering, spectroscopy, optics, and so on, right? Even you can see the geology and applied microbiology, as I said. So in every area, Raman spectroscopy is being used. As far as this publication, year of publication, this I just wanted to show how it is increasing. But here also you can see that, right? From the 1988 to 2020, of course, it is now somewhere around this point. So you can see that how the Raman spectroscopy is useful for the research, and of course it has great application, and particularly in the field of medical science now. A very interesting thing which I have put here is the Raman Open Database. Many of you must be aware that there is the XRD Open Database, the JSPGS kind of thing, right? So now people have developed a database for the Raman spectroscopic study, or rather you can say the Raman data from the materials, and which people use it, right? So, and particularly it is useful in the earth science or the geological science or maybe the planetary science, etc. So people have developed a database where the Raman information or the Raman characterization of material done using the Raman is stored. So this is a very interesting thing which had happen in the case of Raman spectroscopy, right? So that just I wanted to show you the importance, but what it is, right? So it is Raman scattering, as I said. It is inelastic, of course. So when the light falls, there will be inelastic scattering due to the molecular vibration, and you will have the quantized molecular vibration, which is given by this expression in U is equal to nu plus half h cut k omega. There is a classical description of the Raman spectroscopy also, and in this expression, if you see, the higher the m, that is mass or reduced mass, lower is the energy, lower is the mass, higher is the energy. And this also tells us about the bonding nature, right? Because stronger bond, higher K and higher EU. And therefore, the Raman spectroscopy can also be used to understand the bonding characteristic of the material, right? And that is how it is important. The energy in U is in terms of wave number, that is nu is equal to 1 by lambda in centimeter inverse, and that you all see that Raman spectroscopy measurement is normally in terms of the Raman shift, which had the unit as wave number. However, the one thing that comes to the physics part, that is the group theory. So group theoretical, that means, see, when the light falls, there will be a scattering, and based on the molecular vibration, you will get several peaks. But to classify or to assign those peaks, you need to know the group theoretical analysis. That is based on the symmetry or the point group symmetry of the crystal. One use it, and then by using this, one decides that what type of vibration is possible in this particular material or not possible. It can also be decided by the polarization of the light, right? Suppose you take the parallel, you take the perpendicular, and therefore the certain modes will be not active in one case, or in another case, or maybe in both, or maybe possible in both cases. So these things are very useful in assigning. It is not something that is why I said that the physics part physics is important here, because you need to know that how a particular mode of vibration is assigned in a particular material, right? You will have the spectrum, you will have the peak. You can say, okay, this peak is shifting, this peak is getting broader. Those things are correct, but the exact reason of those peaks, that is, which atoms from the molecule or the solid basically are contributing to this. So these things are important, and those things can only be known through the group theory part, and that is where the physics is important. While in other part, people only bother about the band, right? And once they know the band, they can say, okay, this band is possible, this band is not possible, and so on. But when we do from the physics point of view, we cannot ignore the group theoretical analysis of this, right? Because exactly which atom from which position is contributing, right? So you will have the selection rules for Stokes or anti-Stokes Raman scattering to occur. That is what I said. Then the classical interpretation, many of you, it is a classbook, textbook matter. You have mu is equal to this, that is the dipole relation. Selection tells us that when delta L, where alpha is the polarizability. So selection rule tells us that when delta change in polarizability, that is delta alpha with respect to the coordinate is there, right? It is Raman scattering. So there are two things. One, it is the dipole moment of the material, and another, it is the polarizability. Whenever there is a change in the polarizability, Raman scattering will take place. If there is no change, there will be no Raman scattering, right? So the polarizability change with respect to the coordinate for any particular mode will decide whether the material, whether that peak is possible or not, or this Raman scattering is possible from that on. While a complementary technique for this is the infrared. In the infrared, what happens? We do that is and in the case of infrared spectroscopy, it is the dipole moment which is changed. So if there is a change in the dipole moment, it will be infrared. If there is a change in the polarizability, there will be the Raman spectroscopy. The selection rule basically decides the Stokes or anti-Stokes characteristics of this that you can see here. This omega radiation is the relay scattering. This left hand side is Stokes and the right hand side is the anti-Stokes. I said anti-Stokes are blue shifted, Stokes are red shifted, and that is why I have shown in the other color. Right, so these things will happen. Right, you have the electromagnetic radiation. We know it has two components. It has electromagnetic field. It has electric field vectors as well as the magnetic field vectors. Right, and classical interactions of light and matter will give absorption, reflection, refraction, scattering. Scattering, as I said, there will be relay scattering and Raman scattering. So simply what you have a sample, you incident a beam, and several things will happen. Elastic scattering, that is with the same frequency, and inelastic with the change in the frequency. And with nu m, it is not a Vm, it is nu m. So that means it contains a lot of information about the sample, right? This is so Raman spectroscopy studies the frequency change of light due to interaction with the matter. One thing, the energy of the vibrational mode depends on molecular structure and the environment, and therefore it can give you information about the material. Atomic mass, bond order, molecular substituents, molecular geometry, and hydrogen bonding all contribute, and therefore you can get all information from the Raman spectroscopy. The basic problem with this is the Raman signal is 10 to the power minus 6 times weaker than the incident light. Right? And that was the biggest problem for a very long time. But now there are techniques, now nearly 25 different type of Raman spectroscopy exist, right? And in that, the major concern was to increase the Raman signal. And one such methodology is the surface enhanced Raman scattering, and it enhances the signal intensity by many fold, right? And therefore, the problem which was earlier in the Raman spectrometer in terms of signal intensity is now no more, and the people are using SERS, GERS, and many other things to put. As I said, to observe Raman scattering, the molecules must be polarizable, otherwise you will not get it. Right? So you have the matter, incident light, it gets reflected, we are not interested, it gets transmission, we do not. But when it gets scattered, there will be two things, one elastic, another inelastic. In the elastic scattering, you have the my scattering, which takes from the particle. We have the relay scattering, no change. In both cases, no change. In elastic scattering, you have the Raman, right? And it gives you information regarding the phonons, magnons, even now the electrons. Everything can be known from this. Apart from that, there is another scattering that is known as the Brillouin scattering. And the Brillouin scattering is the scattering from the acoustic phonons, right? And since this is a physics seminar, therefore, I assume that many of you must be knowing about the phonon, that you have the optical phonon, you have the acoustic phonon. When you have the optical phonon, it is a Raman spectroscopy. When you have the acoustic phonon, then it is Brillouin scattering. But this Brillouin scattering is also nowadays known as the Raman scattering in the case of nano structures or in the nanomaterial. The point basically is that through inelastic scattering, you can get information about the both types of phonon. Right? This is basically the timeline. In 1871, the Rayleigh scattering was observed, and here 1 by lambda 4, lambda is the excitation wavelength. Then in 1923, it is the Sneckel, Russian scientist, who gave the inelastic light scattering. And then in 1928, C.V. Raman and the Krishnan. Then in 1930, Nobel Prize was awarded to C.V. Raman. Then in 60, the patent of laser, because laser has contributed a lot to the Raman spectroscopy, right? So patent of laser by Bell Laboratory, then 1975, the Sorgin, that is resonance Raman and use of micro Raman techniques. In 2012, more than 25 types of linear and non-linear Raman spectroscopy has been observed. This is anyway first thing which Dr. C.V. Raman observed. Right, so this is a textbook method. I will leave it and then I will go. So as I said, that infrared spectroscopy and the Raman spectroscopy, in both cases is electromagnetic radiation. When falls on the material, gives the scattering. In one case it is dipole moment change, in another case it is the polarizability change. Right. Now here you have selected rule for bias. I think that Dr. Kumar was trying to speak all these things, but let us see. So you have the nuclei, and see, basically what I want to say, that you have the symmetric approach stretch and the asymmetric stretch, right? And this is what is the equilibrium, right? What I wanted to tell you, that if there is a change in del, that in polarizability, right? So this is basically the change in the polarizability. Delta mu by q, that is change in the dipole moment, and this is what basically the delta mu by q. Q is the position, right? So rule of thumb is what? The Raman active mode is symmetric and infrared is more active modes are asymmetric, right? This is something related to the group theory, what I was mentioning, that you have the crystal, in that you have 14 Brabis lattices, then you have the 32 point group, and 14 Brabis lattice plus 32 point groups, 230 space group, and these are the crystal classes: triclinic, monoclinic, orthorhombic. So in every crystal structure, right, the atomic positions are different, right? And therefore, what I told you in the beginning, that by using the Raman spectroscopy together with the group theoretical analysis, you can identify that which atom contributes in which particular peak. So by this group theoretical analysis and considering the selection rule, you can decide that what type of vibrational mode will exist in the particular Raman measurement, and then how this can be interpreted for the material's characterization or the material's property. This is basically the symmetric approach, right? So you can see here that infrared, so change in mu, right? That is how change in mu is taking. While in this case, it is the change in the polarizability. So these all green structures basically tells us that how polarizability is changing. So change in polarizability is Raman, change in mu, that is there. How you do basically for the material science. What we do, we do the synthesis and experimental XRD, that means you synthesize, then you perform the X-ray diffraction to know the symmetry or the group theoretical details of the material. It's like structural details of the material. So you will get the physical structure. Then you do the Raman scattering, you get the peak. So do you have A or B or whatever peak? If A, the single crystal and high performance Raman experiment, you are happy. Polycrystalline and standard Raman, you are still having only peak, So what happens here, that when you have the crystal structure, selection rule determines at the billion zone center, there are methods, a space group and Wyckoff position, mechanical representation, then you will get the infrared and Raman spectroscopy, and then from selection rule Raman tensor matrix, one how we do. At the same time, as I told you in the beginning, that I am basically by training a computational, the theoretical physics, which now is converted into the computational material science, and based on the density functional theory. So you have the, you can use this approach to find out the prediction of the new crystal. And there, this Raman spectroscopy plays a very important role, right? So what we do the theoretical calculation for the structure, then we calculate the zone center phonon calculation, then we use this to have the Raman spectra, and if the phonon modes or the vibrational modes are with the real frequency, that means positive frequency, we can say real frequency, we say that a particular structure can exist, and that is what is basically the crystal prediction. If you get the imaginary, that crystal will not be possible to synthesize in the laboratory in that particular condition in which it was calculated. So it helps by combining all these things, it helps us in predicting a new kind of material. Right? If you want to predict new material or if you want to know more about that. Right? So this is basically the experimental setup. I will not go into this detail. It has a laser, it has CCT, then many other things, and finally we get the spectra. So I will not to go into this. Several types of Raman spectroscopy, right? So these are basically the different types. As I said, and there are 25 different types of Raman spectroscopy now, right? Because it is so important, and you're surprised to know that the life scientists means I mean the medicine, microbiologists, biochemists, and all other, they are now highly using this technique for the characterization. Of course, they do not go into that deep of the group theoretical analysis, but as far as the spectra is concerned, they. But the major problem with the biomolecules or organic molecules is the fluorescence, right? And therefore, by selecting a particular proper laser line and using some other technique, you get very good spectra. And as I said, that most important one and easily available one for many places is the surface enhanced Raman scattering, which suppresses the fluorescence and enhances the Raman peak to a very large level. And you can say basically that each technique is very sophisticated, and as the time progress, we come for the newer and newer approaches. But all these techniques are getting better and better because of the laser, because of the spectrometer, because of the good computational facility. So by combining all these things, we get good instrument or the sophisticated and technique. Right now, I come to the applications of Raman spectroscopy at different length scales. So this is the part which is the topic of this life science and the earth science. See, we can say that everything is material, right? Whether the biomaterial, whether the earth and planetary science material, or whether our real material, right? And this is what is the length scale. It has been shown water is of 10 to the power minus 9 nanometer, and you have the antibody or viruses in the range of 10 to 10 to the power 2, that is 100 nanometer, then bacteria, then the cancer cells, and therefore it is used at every. So initially I will start with the nano and material science. Right, so in the nano and material science, there are many things, but let's basically focus on 2-3 things, right? That is, one is the phase transition, and another is the nanoscience. Nanoscience, what are the important parameters for the nanoscience? That is determination of size, determination of shape, and if it is two-dimensional material, then the number of layers, then the presence, having the defects, etc., etc. So all information can be obtained. So in the nanomaterial, we suppose go one by one. So first is the phase transition, right? So, but in each case, I have taken one example, and that will be given. See, we all know that the material can exist in many phases, depending upon the condition, that means temperature, pressure, and so on. So you have a body-centered material, you have the phase-centered cubic material, then you have the polymorphs of the same material, then you have the different plane or a different crystal orientation in the cases, then you have the stoichiometric changes. So all information, right, can be obtained by using the Raman spectroscopy. That is what basically I mean. I will be taking one, phase and polymorph. Right? It is used in many materials, even we have used, but I will take one example of a material called MAPI. MAPI is methyl ammonium lead iodide, right? It is a material which is recently in focus because of its application to the solar cell. And in the solar cell material, it is perhaps the material which gives the highest efficiency, solar cell efficiency, and that is why it is in focus. But this material exists in different phases. So in at 100 Kelvin, it is in orthorhombic structure that you can see that A is not equal to B, not equal to C. When it is at 150 K, the same material is in tetragonal phase, right? And when at 200 K, the same material exists in the cubic, right? And this is what is the biggest problem with this material. But anyway, we're not talking about this. Just I want to say you that all three phases can be identified by using the Raman spectroscopy. On the right hand side, you can see this is the spectra which is for the orthorhombic structure of the MAPI, right? And peaks are assigned, right? They will, without going into the detail, I give it for you, or you believe that there are new peaks, there is a change in the position, or there is a disappearance of the mini peak, right? So you have 100K orthorhombic, 150K tetragonal, you have tetragonal 2, and then you have the cubic phase. So you can see in the cubic phase you have less number of peaks, and as you go for orthorhombic, tetragonal, etc., it increases. So this Raman spectroscopy can be used for knowing the different structures of the materials, right? That is one thing. Or if suppose I take a particular mode, plot with the temperature, and this plotting of the temperature with the energy of the mode can give us the exact temperature at which the phase transition will occur, exact pressure at which the phase transition will occur. So this is what basically is the application of Raman spectroscopy for phase transition. Here is the crystal orientation, right? You have the NiO, nickel oxide, and you can see here that it is 100 plane, 110 plane, and 111 plane, right? So in all cases, you can see that how intensity basically varies in the case of the different plane. So Raman spectra of nickel oxide for different orientation gives the different spectra, and that can be identified. Here we are not going into the detail of the details with respect to the group theory, and that is why we do not stoichiometry. So you have the Raman shift, so you can know that how the material, that is, this is the Delaphosite, CuCO2 is another solar cell material, and you can see here that as we dope the calcium with 3%, 5%, and the 10%, how the shift is observed in the Raman spectra, or how a new peak is observed. So you can see at all places, like suppose 660 centimeter inverse peak, right? There is a shift, right? It should be here. So basically, it shifts to the lower wave number. 600 peak finally for 10% Ca gets disappeared, right? So this is how a new information or regarding the stoichiometry can be obtained. This is a compound that is basically the platinum pernitride, and this is important because the synthesis of this basically led to the synthesis of nitride materials, and that is why at little later stage you can realize that you have the white LED, blue LED, etc. Of course, those who synthesized this got the Nobel Prize for the blue and LED, blue and white LED, etc. But this is the work basically led to the synthesis of nitride. But what happened when the synthesis of nitride, platinum pernitride, it was at 200 Kelvin with a very high pressure environment, this was synthesized, and X-ray was not able to give the correct information. That is PTN, if it is there, so it is a ratio of PT and N is 1, and the N is very light, or very lighter in comparison to the platinum, and which was the biggest problem in the X-ray diffraction. So this was characterized by using the Raman spectroscopy. You can see here, and synthesis and characterization of the binary noble metal nitride. This work was published in the Nature, and then later on several nitrides. Even now the people are developing new kind of nitrides because it was difficult to synthesize in the laboratory, and this particular work, right, has revolutionized this particular approach. This is anyway our work. So only I wanted to say that Raman spectroscopic measurement help us in indicating that CSCIS, these chains, right? You can see in this particular thing, are retained in gold chloride, even at a compression of 45 GPa. So what it basically was telling that all theoretical calculations were basically telling that it is unstable at 4 GPa, right? But this study was helpful in deciding that it is not unstable up to the 45 GPa, and therefore you can say that gold fluorides might be attackable at lower pressure than the previously proposed. And here you can see that how the spectra with different pressure is basically. Now we come to the nano. As I said in the beginning that nano, this Raman spectroscopy can be a complementary tool for transmission electron microscopy or XRD, because it can give you some information regarding the structure. It can give you the information regarding the size, shape, and all other things. So you can find it all, but here anyway we are taking this as a carbon allotrope, you can say, and you can observe in the carbon allotrope that how the Raman spectra is different. So this is carbon nanowire. You can see that two peaks, and very corresponding to one peak around this 1586 is a characteristic peak. Then you have a sp2 combined carbon allotrope. Then you have the amorphous. Then you have the graphite. Then you have the graphene. You can see that in the graphene and the graphite that how this peak remains at the same right position, but there is a change in the 2700 peak, which is because of a defect. So this is single wall carbon nanotube. This is C60. This is diamond. So for all carbon allotrope, you can see that the Raman spectra is different, and therefore this can be helpful in deciding the many other things about all carbon allotrope. But here, this particular thing is basically used. This particular graph, you can see that graphite. Graphite you have here also. See, there is two peak. One is the G band around 1586, and then the 2D. So it is double of the 1300s, about 1300 centimeter inverse peak, and this is because of the defect, and that is why 2D peak is known. And you can see here that you have one monolayer, you have blue one is the 3 monolayer, then this one is the disorder graphene, right? And because that was a defective, and that is why you can see in the disorder graphene a peak around 1300 centimeter inverse, which is double, and then it goes. You will not find this peak in any other phase, right? And here you can see the graphene oxide, again it is defected peak. In the nano graphene, again defected peak, as well as the G peak, that is at the 1586, which is a characteristic peak of the graphene material, is obtained. So what I mean that you can have the information about the all information about the material, whether it is the number of layers, whether it's the size, and many other things, right? I will show you some other thing. Here you can say doping. So if you have a SnSe2, right, and if you are doping the vanadium, you can see with the X is equal to 0. So this is actual, and as you go on increasing the doping concentration of the vanadium, there is a broadening of the peak as well as the shifting of the peak. So this is how it is useful, right? So you can find out then of course it is not just only I am showing you the Raman spectra. There is a lot of characterization is required once you have the Raman spectra of exfoliated MOS2, right? So this is another very interesting two-dimensional material, and which has been made on PDMS flexible substrate. Substrate means it will have the strain, right? And this strain can be calculated, or this strain can be known. For instance, you see that when you have the 0% strain, right, that means the freestanding MOS2, your peaks will be like this A1G and the E2G. But when you have 0.47% strain, there is a shift in the peaks for both, right, A1G and EG. When you have the 1.21% strain, you can basically see. So it means that, see, the most of the time, whatever material you are developing, this is not freestanding. You need to put it on some surface, and surface basically creates or gives the strain. And this is what is that how with the strain it basically the varies. And then there is a calculation. By calculation, you can know the percentage of strain if it is put on some particular strain. As I said, that you can know the number of layers, right? So this is Raman spectra of few layer MOS2. So it is for 1 layer, 2 layer, 3 layer, 4 layer, right? And you can see here that how the peak is basically changing, how the position and the intensity is changing. And I should tell you that you can know the number of layers by calculating the ratio of the intensity of the two peaks, right? And therefore, if you have the Raman spectra for MOS2, so you can by knowing the Raman spectra and its intensity of the peaks, you can know that how many number of layers are available in that particular sample, right? So that is a very good methodology to characterize this, right? So you can know the stacking, right? So if you have the different stacking, you will have the different Raman spectra, and that is what basically it is. Right nowadays, because when once the many two-dimensional layers have been used and done, then it is the van der Waals heterostructure. Because what happens that when you have the layered structure, it is the van der Waals interaction which plays very important role. So when you make the heterostructure, and that is why it is called basically the van der Waals heterostructure, and it is in fact a new field in the nanoscience. And this you can see that by using the Raman spectra, you can identify the pristine monolayer of 1LG and transfer van der Waals heterostructures annealed for different time and corresponding to the G and 2D peak spectra. So here it is the G band, here it is the 2D band, that is the defected, and you can see that with time and the number of, the heterostructure, how the peaks are, position of the peak is changing, and you can get many information regarding this. This is something related to the phase transition. You can see that it is a compound that is the delafosite compound, right? And this particular delafosite, it is HCOO, delafosite compound. You can see that it exists in two different phases. One is in 2H symmetry of hexagonal structure, and the 3R rhombohedral. And by using, in fact, this is a theoretical Raman spectra calculation using a density functional theory, you can see that how the position of the peak is changing with respect to frequency, and this indicates that there can be a phase transition. But better conclusion you can draw it from here, that if you have the another phase, that is the R rhombohedral phase, you can see that the peak at 600 centimeter inverse basically disappears around 45 or 50 GPa. It means there is a phase transition because a particular peak is disappearing. That means a phase transition, and as I told you, the disappearing or appearing of the phase peaks basically gives many information regarding the phases or polymorphs of the sound form. In this case, this phase transition has been confirmed from many other sources, but this is an indication that there is a phase transition in the case of wave number. Right? This is, I will not go, that is low frequency Raman spectra. I have put it because I told you that there are two types of Raman spectra. One is in the optical region, that is, and another in the acoustic region, that is the Brillouin scattering. So these all are the Brillouin scattering, because this scattering takes place from the acoustic phonon of the solid. And this also gives many information, right? People are using this now for generating the microwave to kill the coronavirus, right? Because if you have the virus, because I worked maybe in 2006, and if you have a virus, that will have a certain vibrational frequency, and if you generate that frequency from the microwave, and if both are resonating, then it can kill the virus. That is what is the fundamental. So this is anyway, it's a Raman scattering from the low frequency region of the spectra. So this is life science. I will take only one or two, and then I will come, because I saw the program. I was to speak only for 20-25 minutes, but I am speaking more because of I was not aware that how much time I will be getting. So you see, in the biological science or in the biomolecules, basically is what there are two things, right? A spectra of biological sample is divided into three regions. One is the fingerprint region, then is the high wave number region, and then the silent region. And this basically helps, right, in characterizing the biomolecules, right? And because we know that this is the fingerprint region, this is the high wave. So if you have any new biomolecule, this fingerprint region will have the different spectra, right? And that is how basically people use it, right? Nowadays, people use it for many diseases. Here you can see that hyperspectral Raman images of malaria infected cell. This is a spectra anyway, but this is how the infected cells of the malaria is seen, right? Then resonance Raman images of cytochrome. That is, this is related to the cancer treatment. Here you can see the automatal. I will by the three color imaging of single HeLa cells in the interface part of the cell cycle using the different high wave number contributions on the spectra. So you can use, see here you have other spectra. See, in the Raman chip, if you have the cell, you have the DNA, you have the cellular protein, if you have the cellular repeats, and if you have the residual. So you can see here that how the Raman spectra is different for different thing in the life science, and that is why it is very important in the life science. Maybe I will show you how imaging is basically done. See, this is the intensity versus Raman or Raman spectra. Here you can see that red ones are the cancerous cell, while blue ones are the normal. In the case of normal cell, there is no peak, nothing. It's very normal. While you have the cancer cell, you get several peaks in the Raman spectra, and that is how. So as I told you, these things are difficult to handle, but the first information basically comes from the Raman spectra. That is, there is a change in the band position, there is an appearance of new peaks, and if there is the appearance of new peak, naturally that is not normal, and that is what basically you can see here, that spontaneous Raman spectra of cancer and normal cells. Here this is the SRS and fluorescence of normal prostate and low grade, high grade metastatic prostate cancers, right? So in the cancer, the Raman spectroscopy is being highly used, right? I mean, of course, it requires precautions, but people are using it. This we have used in Raman spectroscopy in drug delivery, and I will not go into the detail. That it is basically you have we have the oxidized and reduced graphene sheet, and you can see that how the G band and 2 band and their intensity are changing. and change in the Raman spectra following drug stacking. That means electron donating functional group. That means basically the G band will be downshifted, and electron withdrawing groups, that means it is with respect to the attachment of the drug. So electron withdrawing groups, that means upshifted of the G band. And in this case, when you do the better analysis, it is the drug loading mechanism in the pi-pi stacking, right? So it is basically the graphene nano ribbon plus the PLX, which is a cancer drug for the cancer. And when this is loaded, then how basically a shift is observed, and how the peaks are basically reducing, and a detailed analysis tells us these things which I had just mentioned, right? Capsule, that is PLX was. So here you can see the spectra with respect to different graphene oxide. That's graphene oxide plus PLX, graphene oxide, another sample, and so on. So we are basically able to understand the drug loading of on the two-dimensional material or any material by using the Raman spectroscopy. Now just I will go quickly to the earth science and see the Raman spectroscopy for earth and planetary science is very important, because all information and all study in the geological field is time consuming and costly, can disturb texture, introduce contamination, and therefore you require some technique which is simple. So Raman spectroscopy is a fast, non-destructive, and requires little or no sample preparation, identifies both chemical composition and molecular structure. To characterize inclusion with sample, that means the water inclusion can be understood. To evaluate stress within the sample by looking the spectra in the Raman case. That means basically this will tell you that is how the stress is accumulated at a particular time or particular place, and whether that accumulated stress can burst and lead to the seismic or maybe earthquake or not. So this is what is the data I was mentioning. So I will not go. See what we have done, that we took a sample of silicon dioxide, right, and we did high pressure study, and this is the usual. And then when we apply the 4.5 GPa pressure, there is a shift of 36.64 centimeter inverse on the silicon dioxide. That means why we did it. So silicon dioxide, that means we know that it is rate and all other rate simply, and in this region everything is this component is basically the silicon dioxide. So we consider, okay, if you go for the 10 feet deep or maybe 100 feet deep, in 100 feet deep or a 10 feet deep, there will be pressure. So if you have a pressure, naturally the structure will change, and that is what it happens. So when you have the silicon dioxide on the surface, it is a normal, a very prominent peak, 464 is characteristic peak. But when it goes to a 4.5 GPa pressure at a certain depth, you can consider it will have a shift of 36.64, right? And therefore it can give several information regarding the material within the core or the mantle, or in fact at any depth of the in the earth. Similarly, it can give you information of the planetary material, that is the aerosol and all other things, right? So this is a fault zone, right? Gujarat is a very sensitive place for the earthquake, and of course our place is also very sensitive. And this is a quantity. This is called basically a fault zone. That means this is something which represent that something might have happened maybe in the thousands or 2000s or lakhs of years before. And anyway, because I don't know whether people at our side do or not, but here I have seen with the geological people, they survey and they find the places where this kind of fault is obtained, right? So what was our purpose? That we took sample from maybe any position, maybe here let us consider, and then at this position, right? So these are the basically sample collection. Then we performed some calculation, and then we took the Raman spectra, and then by using that we could find the stress accumulated, right? And that was a very good contribution that geologist basically tells us that what will be the stress. This is fluid inclusion. That means memories of the parental liquid state trapped in crystal during magma evolution, or maybe anything in the earth. We know that at certain depth there is a water, so we need to know that what kind of material is there which basically transport the water. And so that is basically the inclusion, you can say. Here it is talking about the volcanic eruption and all of that thing. So fluid inclusion is a glass inside a crystal, and therefore Raman spectra can give you the information regarding the presence of the inclusion. And that is what you can see here in this uh, case, that you have the raw spectra, you have the mineral spectra, and then by subtracting you can get the fluid inclusion Raman spectra. So Raman spectrum of the inclusion can be obtained easily by subtracting, right? Subtracting the spectrum of the mineral host from the raw spectrum, right? So that is what this is pressure, temperature, depth profile. So you have same silicon dioxide, and you can see that this is pressure, this is temperature, this is depth, and this is at everywhere. And depending upon the depth, depending upon the pressure, depending upon the temperature, you get a different type of structure of the same material, and that can be reflected in the Raman spectra, which is put in the right panel, right? So first one is the SiO2, then the cristobalite, tridymite, coesite. So these are all basically the information which you can get from the Raman spectra performed. Or what you can do, you collect the sample from such a depth, and then you do the Raman spectra, or you take the material at of normal condition and apply that much pressure, and then you perform the Raman spectra, so you will get the information regarding it. This is in the art and Raman, that is art and Raman spectroscopy. Suppose these are the mineral based unique pigments were popular among the Indian artists of the medieval India during 17th century. So the samples were collected for different location, and then the Raman spectra was taken, and you can see that when sample was collected from A, you have this, in the B this, and then C, D, E, and this is basically the intensity was low, so that is why it is multiplied. But you can know that what sort of pigment is basically used in those painting, right? Or those art, right? So art and is being used in the Raman spectroscope. Raman spectroscopy is used in the art and archaeology. Similarly here, right? Again, you collect from the different position and take the Raman spectra. You can see A, B, C, D, etc. Right? So it is how it is used, right? It is again the similar thing. Raman study of rock shelter paintings at World Heritage Site at Bhimbetka. It is in MP, that is close to Bhopal. So people collect it and then identify the presence of this thing. For instance, in A and B, in A the photograph of a flower in shelter, in the B in situ Raman is no white pigment in rock shelter, right? Raman bands correspond to calcite, gypsum, another quartz. So you can identify that what kind of pigments are basically used in this particular thing, right? So I will not go into this part. I stop here, and thank you very much for listening. It might have been a bit lengthy, but that is what I prepared. Whatever I prepared, I have just conveyed. If you have anybody has any question, you can ask me, or if not, then you can send me the question from the email. I will answer it. Right? So right? So thank you very much. Oh, 73 questions are there. Yes, there are. I see some question. Uh, so one is by Bal Mukin. Can you hear me? Are you? I'm audible. Okay.
Yes, sir.
So
You're
I
audible.
see many questions, but if possible, please send your PPT. Sure, I will send. Right. One question is Bal Mukund Mishra is asking in that yes, you can use the Raman spectroscopy for better result. See that X-ray is also important. The Raman spectroscopy is also important. Right. So it is not that the X-ray, so the Raman spectroscopy will complement, or I mean, it will replace the XRD study. It is useful for complementing and then several other information. But certainly you cannot get the lattice parameter from it here. You cannot get the coordinate. You cannot get many other things, right? So you can use it for help, right? Then I now don't move it. Why the Raman spectrum is not applicable in metallic surface, right? See what happens in the metallic surface. You have the free electrons, right? And that basically is not allowing to have the spectra. See, when you have the metal system, free electron, that means a lot of this you can say that surface plasmon resonance kind of thing will happen, and you will not get. So you don't get the good Raman spectra in the case of metallic surfaces or metal thing. Then recent feedback between the registry. Right, okay, this was all very general thing. So, but anyway, if anybody has any problem, any question, you please don't hesitate. You ask me, right? I will use it. I mean, I will try to answer your question because this is a very versatile methodology to characterize the material. So, whenever if you have any problem, please don't hesitate and you ask me by mail, right? Because I don't. I see many general questions, right? So, and anyway, I will send my PPT as he has asked.
Vibhuti
Right?
sir.
I can leave meeting now.
अजीत सर,
हाँ,
अजीत सर, प्रफुल्ल सर ने अपना लेक्चर समाप्त कर दिया है. अजीत सर,
मैं हेलो.
यस सर.
हाँ, मैं डॉक्टर प्रफुल्ल कुमार झा जी को बहुत बहुत धन्यवाद देता हूँ. उन्होंने विषय को बहुत अच्छी तरीके से ऐसे टीचर के रूप में रखा और बेसिक फंडाज से लेके रिसर्च से फील्ड में और इसके यूटिलिटी और किस तरह से रमन इफेक्ट ये इफेक्टिव है. इलास्टिक, इनलास्टिक स्कैटरिंग और रिलेज स्कैटरिंग, रमन स्कैटरिंग, डेप्थ ऑफ स्पेक्ट्रा, लाइफ में जो चाहे ये सोशल लाइफ हो या इधर लाइफ साइंस में किस तरह से यूटिलिटी है, इन्होंने जो विषय वस्तु को रखा और हम लोगों को जो मटेरियल मिला, ये बहुत ही उपयोगी होगा हम लोगों के लिए और छात्रों के लिए भी। मैं सर से आग्रह करूंगा कि एक हार्ड कॉपी जरूर हम लोगों को मेल पर भेज दें या हार्ड कॉपी भी भेज दें, जो उसका हम लोग उपयोग कर सकेंगे।
हाँ, नहीं नहीं, अवश्य 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 मैं भेज दूंगा। और
जी जी,
ये प्रेजेंटेशन तो मैं सॉफ्ट कॉपी भेज ही देता हूँ। आई हैव
ठीक।
द।
और रियली सर, हम इससे पहले सुन नहीं पाए थे, हमारा फर्स्ट था और हमको बहुत ही अच्छा, और प्लेसिंग जो आपका था वो काबिल तारीफ था। और एक फिजिक्स न जानने वाला भी इस विषय को बहुत अच्छी तरीके से कैच कर सकता था। इसके लिए मैं आपको धन्यवाद देता हूं, और आपने जो इसे जुड़ा उसके लिए भी आभार प्रकट करता हूं मिथिला यूनिवर्सिटी के तरफ से।
ठीक
अब
ठीक
मैं चाहूंगा कि हमारे जो कन्वेनर हैं डॉक्टर विभूति शेखर लाल दास जी, मैं भी इनको भी साधुवाद धन्यवाद देता हूं कि आज जो परिस्थितियां है उस परिस्थिति में बिना डिस्टर्ब हुए फिजिक्स ऑनर्स का एक ग्रुप हर सेशन में रहता है, जो दिन रात लेबोरेटरी से लेके प्रैक्टिकल पेपर तक जुड़ा रहता है। और मिथिला यूनिवर्सिटी में और बाहर भी यहाँ के छात्र बहुत अच्छा कर रहे हैं और डिफरेंट फील्ड में जा रहे हैं, और ये दिन रात इस जुड़े हुए रहते हैं। इसलिए इनको अपने विभागीय कलीग को लेकर के बहुत बहुत धन्यवाद देता हूँ। अब मैं आग्रह करूंगा कि ये ओवरऑल अप्राइजल, आपका अप्राइजल क्या ये हो सकता है, लेकिन ये कंक्लूजन में कुछ हम लोगों को बीच रखेंगे डॉक्टर विभूति शेखर लाल दास जी।
विभूति सर का माइक ऑफ है। अजीत सर,
जी यस,
विभूति सर का माइक जो है ऑफ है, उसको ऑन करने।
अच्छा ऑन कर।
विभूति सर क्या सुन पा रहे हैं क्या? हाँ सर, अभी आ रही है। आवाज आ रही है? आवाज आ रही है?
हाँ, आवाज आ रही है।
Respected Chairman, Professor Vidyanath Jha, distinguished guest speaker, Professor Prakul Kumar Jha and Dr. Uday Kumar, colleagues of the Physics Department and Mlsm College, Darbhanga, honorable participants of this webinar. Just now we have heard a related lecture on the topic Raman Spectroscopy for material science and emerging field in the physical science from two distinguished speakers, Professor Prakul Kumar and Dr. Uday Kumar. As is evident from their deliberations on the topic, Dr. Jha and Dr. Kumar, both scientists, are experts in the field of materials. Professor Jha showed the light of the Raman techniques and theoretical aspects of Raman effect with spectroscopic techniques involved in analyzing the materials prepared by the combination of different elements and their bondings at molecular level. Dr. Kumar told Raman scattering is a phenomenon in which event photons lose or gain energy by interaction with vibrating molecules in the sample. Energy shift is used to explain information regarding molecular combination in a sample with high accuracy. This scientific knowledge is used Professor Jha expressed the applications of Raman spectroscopy not only in material science and in physics, chemistry, rather it has some applications in biological science also, just as in cancer diagnosis or in preparation of microwave to harm coronavirus disease. This spectroscopy has wide applications. So I again request both the speakers to send their lectures in hard copy or in our mail. Thank you for all the participants, and our chair, with the permission of Chairman Ajit Kumar, Professor Ajit Kumar Chaudhary, will propose vote of thanks.
अब हम उदय कुमार जी का ये डिस्टर्ब हो गया, उनसे आग्रह होगा कि वो हार्ड कॉपी हम लोगों के बीच भेज देंगे, उसको हम लोग शामिल करेंगे, उसका अधूरा सुन पाए। मैं सबसे पहले अपने इनवाइटेड डिस्टिंग्विश्ड गेस्ट ऑनरेबल प्रोफेसर प्रफुल्ल कुमार झा of MS University of Baroda, very famous place of India, Dr. Uday Kumar of NIT Jamshedpur, अब हमारे एमएलएसएम कॉलेज के प्रिंसिपल जो चेयरमैन हैं के सभी का हार्दिक अभिनंदन स्वागत करता हूं और विशेष रूप से धन्यवाद ज्ञापन करता हूं कि उदय कुमार जी का ऐतिहासिक इन्होंने जो विषय की स्पष्टता को रखा, उसके लिए बहुत बहुत धन्यवाद और अपना बहुत समय दिए। मैं चाहूंगा कि हम लोगों को सहयोग करते रहेंगे और कुछ को डिस्टर्बेंस नेटवर्क के कारण कोशिश करूंगा कि आगे नहीं होगी। मैं अपने चेयरमैन डॉक्टर विद्यानाथ जी, इनका अपना ओरिजिनल फील्ड जो है सो मखाना का क्षेत्र है, जो मिथिला के में है, जिसके लिए परिचित है। माछ मखाना में इनका बहुत ही उत्कृष्ट योगदान है क्षेत्र में। उनको बहुत बहुत धन्यवाद देता हूँ कि इनको विशेष इंटरेस्ट रहता है इस तरह के काम में, से ज्यादा से ज्यादा हुए सेमिनार और कोरोना के बाद हुए वेबिनार ये बात विचार में बराबर विभाग को उत्साहित करते रहते हैं। और की बात कार्यक्रम के डॉक्टर विभूति शेखर लाल का, जो हमेशा 24 घंटा भी अपने विभाग के लिए समर्पित रहते हैं और छात्र में काम करते हैं, उनके लिए उनको भी धन्यवाद देता हूँ। और मैं विभाग के शिक्षक डॉक्टर SMA नुमानी, डॉक्टर अशोक कुमार, डॉक्टर प्रदीप कुमार झा, डॉक्टर सतीश चंद्र ठाकुर, डॉक्टर लक्ष्मीकांत झा, डॉक्टर राजकुमार चौधरी, सुधीर जी, सभी को विशेष रूप से धन्यवाद देता हूँ कि इन्होंने इस वेबिनार को सफल बनाने में और अपना बहुमूल्य समय दिया और जो विशेष इनकी भूमिका रही। मैं धन्यवाद देता हूँ सभी पार्टिसिपेंट्स को जो हमसे जुड़े, उनको ये देता हूँ, धन्यवाद देता हूँ। विद्याशंकर जी को धन्यवाद देता हूँ और यहाँ के जो कुछ अनुज जो कि ये टेक्निकल एक्सपर्ट्स है, यहाँ देखता है काम को, उसको धन्यवाद देता हूँ। इसमें और भी महाविद्यालय में शिक्षक हैं, जैसे डॉक्टर सतीश कुमार सिंह जी, अवधेश मिश्रा जी, डॉक्टर माधव चौधरी जी, सभी को विशेष रूप से धन्यवाद देता हूं कि ये बराबर इस महाविद्यालय में ज्यादा से ज्यादा वेबिनार का आयोजन हो कोरोना काल में, तो उसको विशेष रूप से धन्यवाद देता हूं। और यहाँ के कर्मियों को भी जो बराबर सहयोग करता रहता है, उन सभी को धन्यवाद देता हूं। और अतिथियों ने जो समय दिया और पार्टिसिपेंट्स जो जुड़े, उनको विशेष रूप से धन्यवाद देता हूं कि इस कोरोना के समय में और खास करके मिथिला यूनिवर्सिटी या उससे बाहर लोग कोरोना का ये कुछ श्राप भी अभिशाप हो जाते हैं, ये देखने में मिला कि वेबिनार का प्रचलन खास करके इस रीजन में नहीं था और लोग मोबाइल और लैपटॉप का उपयोग करके पढ़ना का प्रैक्टिस नहीं था। ये समय ने, प्रकृति ने अब इसको इतना फेमिलियर बना दिया कि अब बच्चे भी पढ़ रहे हैं। यहाँ इधर भी सुदूर एरिया, देहाती एरिया में तो कुछ बुरा का भी अच्छाई आ जाती है, उस दिशा में हमको दिखाई दे रहा है। और सभी को बहुत बहुत हार्दिक बधाई, धन्यवाद, प्रणाम। अब अध्यक्ष की अनुमति से कार्यक्रम को समाप्त किया जाता है।
और फीडबैक फॉर्म के लिए हेलो, आप लोगों का जो फीडबैक फॉर्म है अभी मैंने डाल दिया है।
हाँ उदय जी, फीडबैक जो है हम एक चाहेंगे कि फीडबैक सभी पार्टिसिपेंट्स भेज दें जिससे कि सर्टिफिकेट इशू किया जा सके।
और फीडबैक का लिंक जो है मैंने अभी कन्वर्सेशन में डाल दिया है, उसको क्लिक करके ले लें, या फिर अभी उसकी थोड़ी देर पहले मैंने जो एक लिंक प्रोवाइड किया था व्हाट्सएप ग्रुप का, मैं उस ग्रुप में भी इस फीडबैक लिंक को डाल देता हूँ। ठीक है,
ठीक है विजय शंकर जी, तो
ठीक, डिस्कनेक्ट करते हैं सर।
ठीक है, एंड कीजिए।
नमस्कार सर।
नमस्कार।